So we've looked at molecular orbital diagrams for diatomic molecules, but so far we've only looked at homonuclear diatomic molecules. Diatomic oxygen, dioxygen, diatomic boron, diboron, diatomic hydrogen. What happens when you have an unsymmetrical diatomic? For example, hydrogen fluoride, HF gas. Lewis structure would have you looking like that. Hydrogen bringing a single electron, fluorine bringing 7 valence electrons and 1 unpaired electron, and simply forming a bond. So you would predict a bond order of 1, a simple single bond. You would predict sp3 hybridization and tetrahedral electron pair geometry around fluorine with 4 electron groups, and of course, hydrogen can only ever be linear because it only ever has 1 bond, a duet rather than a octet. What would the molecular orbital picture look like for HF? We know that it has a large dipole moment with fluorine having a very large tendency to draw electron density towards itself because it's the most electronegative element on the periodic table. And our understanding of the orbital picture, the bonding in HF, should account for that. The first thing we want to ask ourselves is how many molecular orbitals are there for hydrogen fluoride? Hydrogen brings just a 1s orbital, but fluorine brings a 2s orbital and a px, a py, and a pz orbital in its valence shell. So in the valence shell, we have 4 orbitals coming from fluorine, and we have 1 orbital coming from hydrogen, 4 atomic orbitals. Or sorry, 5 atomic orbitals total. Means we must have 5 molecular orbitals for the hydrogen fluoride molecule. 3 of those orbitals, the 2s orbital on fluorine, the px orbital on fluorine, and the 1s orbital on hydrogen, have sigma symmetry. Whereas the other 2 have their electron density above and below the bond axis, and they have pi symmetry. And once again, py and pz have pi symmetry, but they have different symmetry from each other because one has a node at y equals 0, the other one has a node at z equals 0, so they can interact with one another. What that means is that they will become non-bonding pi orbitals. Py will simply be relabeled pi y, and pz will simply be relabeled pi z. But since they haven't changed in energy, or indeed in shape, or location, they won't contribute either to the bonding or to antibodies. And that's what usually happens when you have a lot of lone pairs, is that you have non-bonding orbitals. So if we draw the hydrogen 1s orbital, and we draw the fluorine 2s and 2p orbital energy levels, we might find something that looks like this. We know we're going to have a large delta E for fluorine, because it's to the right of oxygen, which means that the energy gap between the 2s and the 2p orbital energy level is quite significant. And we know that the hydrogen 1s orbital, because of a very small nucleus, is pretty high energy, probably higher in energy than the 2s orbital on fluorine, because even though the 2s orbital on fluorine extends much further from the nucleus than the 1s orbital on fluorine, it's got a really big nucleus. The 2s orbital on fluorine probably does not extend further out than the 1s orbital on hydrogen. So we don't have to worry about the 2s orbital and the 2p orbital mixing with each other, but we do have to worry about both of them potentially mixing with the hydrated 1s orbital. Py and Pz are just going to come straight over and be Iy and Iz. No change in energy at all, non-bonding orbitals. So my challenge is to take these three orbitals, 2s and 2px on fluorine and 1s on hydrogen, and from those form three new molecular orbitals. Well, there are four possible combinations that you can make from those. You could take the wave function on the 1s orbital, add it to the wave function on the 2s orbital. You could take the wave function on the 1s orbital and subtract from it the wave function on the 2s orbital. And you could do the same two linear combinations for the 2px orbital. This is four combinations though. And the rules of molecular orbital theory tell us that we can only make three molecular orbitals from those three atomic orbitals. So this is a problem. We can't have all four of these. So let's take a look at what those would predict, right, if we were to do those four combinations. And what we will discover is that these two combinations, the destructive overlap with the 2s orbital and the constructive overlap with the 2px orbital, turn out to be degenerate solutions. These two combinations predict the same molecular orbital. So we actually only really have three different combinations: constructive overlap with 1s and 2s, destructive overlap with 1s and 2px, and then this degenerate solutions that can be arrived at either by destructive overlap with 1s and 2s or constructive overlap with 1s and 2px. So let's see what those would look like. We know that the lowest energy orbital is going to look mostly like the 2s orbital on fluorine. There's going to be a larger contribution. So if we were to do it with coefficients to scale, it's going to look something like that, where the 2s orbital on fluorine, because it's the lower energy, makes a bigger contribution than the 1s orbital on hydrogen. So what we're going to have is something like this. The inner lobe is really not relevant, so we don't have to consider it. And that's going to lead to an orbital that is no longer symmetrical with respect to the two nuclei. That's going to lead to an orbital that is mostly over here on the fluorine. Something like that. Because the 1s orbital is not making a very large contribution. So these lowest energy orbitals, or lowest energy electrons, are mostly on fluorine. We'll call that sigma 1. It's below the 2s energy level and below the 1s orbital energy level, but closer to the 2s. But since we've used up a lot of the 2s orbital now, there isn't as much left. So we're either going to take a small amount of that and interact it with the 1s orbital on hydrogen, or correspondingly, we could take a smaller amount of this I1s orbital and interact it with a fairly large amount of the 2px. So this would look like this. Fairly large 1s orbital on hydrogen, overlapping with a 2s orbital, but a relatively small 2s orbital, creating a new node and predicting an orbital that leans towards hydrogen, with a new node here and leaning over towards hydrogen a little bit. If we did this, we would have our 2px orbital and we would have it overlapping constructively with our hydrogen orbital. Notice we predict exactly the same thing. The position of the node might be slightly different, but we predicted a fairly large lobe over here on the hydrogen side, and a fairly small lobe over here on the fluorine side with a single node. Whether you get to it by destructive overlap with the 2s orbital on fluorine or constructive overlap with the 2px orbital on fluorine, you predict the same thing, a single node orbital, sigma 2. And you predict a lot of electron density between the nuclei. So it's a bonding orbital. It's lower in energy overall than the orbitals from which it came, and I probably put it too high. Probably ought to put it more like here. And then the last possible combination would be the 1s orbital, right, which there's not that much left in it anymore. Destructively overlapping with a fairly large coefficient on the 2px orbital, because we really haven't used very much. In reality, we're actually combining the 1s, the 2s, and the 2px orbital all together to make this sigma 2. Sigma 2 takes components from 3 locations, whereas sigma 1 takes most of it from here and a little bit from there, and this one, right, sigma 3 takes a little bit from there, but mostly from the x, and none from the 2s. So we don't get the same, sigma 2 is the only one that has lines connecting with all 3. This coefficient larger, more 2px orbital than there is 1s orbital. So that is a sigma 2s orbital or 2p orbital overlapping with the hydrogen, creating a new node, having its existing node, and therefore having an overall shape has a new node here, an existing node here, and because this new node is between the nuclei, it's antibonded. So that would be our orbital energy diagram. Sigma 1, sigma 2, and sigma 3. These 3 energies have to add up to the sum of 1s plus 2s plus 2px, and then pi y and pi z coming directly over from py and pz as non-bonding orbitals. And now we're going to put our electrons in, 8 electrons, which basically means filling the first 4 orbitals and leaving sigma 3 empty. Sigma 1 leaned heavily towards fluorine. Pi y and pi z are exclusively on fluorine. So only sigma 2, right, has significant electron density on the hydrogen atom, which means that 6 of the 8 electrons spend most of their time on fluorine, which is exactly what you would predict by looking at the molecular dipole and showing that that's a very polar bond with most of the electron density lying on fluorine and only a little bit on hydrogen. The only orbital that has the majority of its electron density on hydrogen is empty. There's nothing in that one, right? Sigma 2 has a little bit more electron density on hydrogen than it does on the fluorine, right? We predicted that it was a little bit more electron density on hydrogen than fluorine. But there's only 2 electrons in that orbital. So there's 2 electrons spending more time on hydrogen than fluorine than 6. So we've correctly predicted that the bond order correctly predicted that it should be a single bond. This is an anti-bonding orbital. Actually, I guess we predicted it should be a fairly short, strong bond, right? 6 bonding, well, let me restate that, right? 4 non-bonding electrons. So we've got 2 bonding electrons and 2 anti-bonding electrons. But the bonding electrons drop in energy a lot more than the anti-bonding electrons rise, which means that the bond order isn't really 0. Right? The bonding electrons are much more effective at bonding than the anti-bonding electrons are at anti-bonding. Right? And we predicted that most of the electron density should lie towards fluorine. So that was fairly easy, relatively speaking, because one of the atoms in the heteronuclear diatomic was hydrogen and only brought 1 electron with it, or 1 orbital with it, right, the 1s. What happens if you have an unsymmetrical diatomic where both are second row atoms, like carbon monoxide or nitric oxide, where you have 8 orbitals to consider?